Thank you, Stefan. Can everyone hear me? So thanks to the organizers for giving me a chance to speak here. I'm giving a in-person talk after 3 years, so I thought I'll make it a board talk. Okay. So I'll be speaking about joint extreme values of L functions. This is joint work with Lukas Pankowski and Kamlaksha Mahtab. So as we saw in the previous talk, we saw about the Riemann Zeta function. So we have this critical strip for the Riemann Zeta function. We saw that it has a functional equation between relating values at s to 1 minus s. So basically everything interesting is happening inside this critical strip from 0 to 1. And what we are interested in, so our interest is in the following. We wish to study the behavior of zeta s on a given vertical line real part s equal to sigma in this critical strip. Okay. So let us say I fix a sigma inside half and 1 due to the so we have this critical line, and we may look at between half and 1 here. Let's take any vertical line here that we are looking at, and we want to look at the behavior of zeta on this. So what is known, let me write. Okay. So it is known that zeta of sigma plus it, the magnitude of this, it becomes, let's say, as t varies over real numbers, this becomes, this is unbounded, so you can make it arbitrarily large. You can also make it arbitrarily small. So this is known. Arbitrarily large or small. What we wish to do in particular is quantify this. What do we mean by arbitrarily small and arbitrarily large in terms of this t? Okay. So we want to quantify this in terms of the ordinate t. Now there are two ways to do this. So there are two ways to do this. One way is we obtain some big O bounds. Okay. So for example, I think everybody here knows what is a big O bound. Let me just give an example of something like this that comes up. For example, Riemann hypothesis would imply that log of zeta sigma plus it would be of the order log t raised to 2 minus 2 sigma by log t for sigma inside half to 1. Okay, we are taking closed interval half, closed on the half side to 1. So this is an example of a big O bound, which is known. So what this means is for all t sufficiently large, after some point, this Riemann zeta value is bounded by a constant times whatever you have on the right side. So these are examples of big O bounds. Second thing that we may do are what are called omega bounds. So if we give an example of this, the first such result was by Titchmarsh. Yeah, so actually there is a way to define the log. Let me see if, let me write something. What we do typically is, suppose I want log of this value, okay? Not right now, let's just say log of that value, not log of zeta of that value. What we do is we know on, okay, let me say maybe log of zeta of this value, whatever it is. We take this horizontal line, okay? And whatever is that y equal to constant line, that we look at it on the real right side of 1, okay? Here we know the values of log because there you have the Dirichlet series, you have the series for log. So you will continuously vary it. There is this method of continuous variation by which you can come, just like how we define argument, you know, you can go continuously from here to here. This value is fixed. So you take, that way you go to this. If it is 0, this is if it is non-zero. If it is 0, then you can define if zeta of sigma plus it is 0, then you can define this by a limit process. So you can do something like half limit of log sigma plus it plus epsilon plus log zeta of sigma plus it minus epsilon. Okay, this whole thing ka limit you take as epsilon goes to 0. So you can do this and define log. So we can, yeah. So this is an example of a big O bound, and now I was giving example of an omega bound. So this is fine. Closed interval at half. So it is stronger. It is there at half also. Open is also true. Is it fine? We are assuming Riemann hypothesis. I'm getting that. So these are known results. Omega bound is given, for example, by first omega bound was given by Titchmarsh for the Riemann zeta function. So what it says is for any sigma, again inside half 1 and any epsilon greater than 0, we have zeta of sigma plus it is greater than exponent of log t raised to 1 minus sigma minus epsilon. Okay, this holds for arbitrarily large values of t. So typically an omega bound is, see, when we say an O bound, we are giving a bound after which, it behaves like an upper bound for all the ordinates t. For an omega bound, what is happening is the magnitude of this zeta function is hitting this right-hand side infinitely often. Okay, so it is at least that much up to some constant, depending on the way we write it, infinitely often. Omega bounds are thought to be closer to the actual behavior of zeta. If you see, there is a gap between these two bounds. This is 2 minus 2 sigma, this is 1 minus sigma. So in this talk, we will focus on omega bounds. So let us focus on omega results. So let me just state some of the known results. In 1977, Montgomery showed the following. So let us fix sigma between open half and 1, okay? And let capital T be sufficiently large. So now we are also kind of saying in every strip from ideally from T to 2T, how often something happens. So we are saying now there exists T inside capital T raised to sigma minus half by 3 to T such that this magnitude of Riemann zeta at sigma plus it is greater than or equal to exponent of 1 by 20 sigma. So we'll have, okay, let me write. There is the same behavior that we are observing. This log t raised to 1 minus sigma. Instead of epsilon, what he's getting is at the bottom a log t raised to sigma. And there is this constant type thing here, sigma minus half raised to half. Okay. So this happens. So what we are saying, what he's saying is in every strip from t raised to some power to capital T, there is a value of the ordinate small t such that zeta takes a large value inside that strip. This can be extended to sigma equal to half under the Riemann hypothesis. So under Riemann hypothesis, but obviously this term will change. So there is a different constant. And also better range of T. So this strip can be made, I think, slightly smaller. Okay. Yeah. This sufficiently large thing. This equal to this. I don't know actually. You mean in that strip, in each such strip? I don't know. Okay. All right, for sigma equal to half, maybe I should just say a few more things. This result, which is under GRH, was made unconditional by Balasubramaniam and Ramchandra. So there are some, they made this part unconditional. And there are also currently the best known such result for sigma equal to half, the best bound is by Bondarenko and Stipe. There are also refinements due to Della British, I don't know how to pronounce this, and Tenenbaum. Okay. So let us see what else is done. This is all for the Riemann zeta function. We may ask about other L functions. So for other L functions, we have the following results. We have, so this was greatly generalized to a class of Dirichlet series having real coefficients satisfying some analytic and arithmetic conditions by Shankar Narayan and Singh Gupta. So this is Dirichlet series with coefficients in R plus some analytic and arithmetic conditions. Yeah, this is the problem actually. I got this one right? This is wrong. Yeah. Yeah. Fine. So thanks. So we have this broad generalization, and recently there is also work being done on the Selberg class, So we have results of Pankowski, Pankowski and Steuding in 2013, where they looked at this phenomenon for functions in the Selberg class. So what we will do today also will involve the Selberg class. So I think it will be best if we give a definition of this Selberg class. So maybe I will write it here. So we'll denote the Selberg class by this curly s. And what we will say is a meromorphic function. We won't write it in too much detail. Many of you may have already seen it, but we'll just state out the properties. So a meromorphic function L is said to belong to S, to this Selberg class, if it satisfies the following axioms. So this class of functions was axiomatically modeled by Selberg, and he thought the idea was that it would capture all the functions which are naturally coming from arithmetic and geometry. And yeah, so they all have some nice properties. So first property, so if let us say if LS satisfies the following, we want a Dirichlet series. So we will write LS to be summation of, sometimes we want to emphasize the L function, so we will write AL, but otherwise we may sometimes just write A of n. This we have such a Dirichlet series which is absolutely convergent for real part S greater than 1. This is your first axiom. Second axiom is analytic continuation. So what we will say is there exists a non-negative integer such that s minus 1 raised to m, when you multiply by this L function, it becomes entire and it has finite order. Third thing is there is a functional equation which we will not write down. It is similar to what we have for the Riemann Zeta function, but it relates LS to L1 minus S power conjugate. Okay, so this is how the relation works, and similar kind of function, it's an analog really of what you have for the Riemann Zeta function, but there will be more, there can be more gamma factors. Okay, so we have multiple gamma factors also in the functional equation. Okay, then we have what is called the Ramanujan hypothesis, which is a growth condition on these coefficients an. So it tells you that these coefficients are of the order n to the epsilon for any epsilon positive. Okay, and finally, yeah, I should not cross this line. So I'll write it here. Finally, we have Euler product. So okay, so these are the 5. If your L function, it's a meromorphic function which satisfies these 5 conditions, then you say it is an element in the Selberg class. What we will be concerned with is this 5th condition. We will actually be replacing it with something stronger. So let me call that 5 dash. That is called the polynomial Euler product. So in the original condition 5, the each product in your Euler product it need not be a polynomial. It can be an infinite series. That's how it is framed. Here we are truncating that. We are saying it's of polynomial type. So we have, more precisely, I'll write down 5 dash. We have that L should look like product over prime numbers. Each Euler product for that prime looks like J going from 1 to R. We have something like 1 minus some coefficient depending on this P raised to S inverse. So this is more familiar to what we are used to with the Riemann zeta function, but there might be many of them. Okay, for some natural number R and this nu J, P is some complex number. Okay, so when your L function satisfies these conditions 1 to 4 plus 5 dash is stronger than 5, then we say that this is inside the Selberg class with polynomial Euler product, which we will denote as S poly. Okay, so this is a sufficiently large class. Many examples of functions we already have in this class: the Riemann zeta function, Dirichlet zeta function, Heckel functions, etc. And it is also conjectured, whatever we know in the Selberg class, it's also of polynomial Euler product type. So it is conjectured that this S poly should actually be all of S. Okay. So hopefully we are not losing anything if we assume this. Also, what is known is that, let me start here. So there, Selberg made some other conjectures for elements of this class. These are known as the Selberg orthonormality conjectures. So we will just frame that before we try to state our main result. So we have this S has a semi-group structure. So it turns out to be a semi-group under multiplication. Means there is closure under multiplication. You take two L functions in the Selberg class and multiply them. The resulting product is also in the Selberg class. And there is identity also in here. Just your 1 is the identity, right? So this is a semi-group under multiplication with identity. So we can talk about irreducible elements inside the Selberg class. So we say irreducibles in S are called primitive. That means it cannot be factored any further inside this Selberg class. And the Selberg orthonormality conjecture concerns these primitive elements of the Selberg class. So what is this Selberg orthonormality conjecture? So we will state this, we'll call this as SOC. What happens is, we are saying, well, he conjectured that these primitive elements in the Selberg class, they sort of behave independently of each other. So if you take two distinct primitive elements, they will be orthogonal. But if they are the same, then they'll align. So how we frame this is, you take, actually this won't be, this is not the actual way, the way I am stating it is a stronger version. So let me write down strong version of Selberg orthonormality conjecture. So we take L1, L2 inside this Selberg class, and they are both primitive. Then we have the following. If you look at this product of coefficients of L1 and you take the coefficient of L2 at primes, take its conjugate and run over primes up to x. So what happens is, suppose L1 and L2 are the same L function. Then what we would get is the following. If they are the same L function, let's say if L1 equal to L2 is equal to L, then we would get summation P going up to X, absolute value of ALP squared, which he conjectured should behave like a constant or average. So you should get something like some constant kappa depending on L, and number of primes up to X you will count, you will get lie of X plus an error term. So you will get X by some powers of arbitrary powers of log X. So we will say for any A positive, you get this. On the contrary, if L1 and L2 are distinct, then you get, they are believed to be orthogonal to each other in the sense that you get a lot of cancellation in this sum. So you will get big O of X by log X to the A if L1 not equal to L2. So the actual ortho, I'm calling this the strong version. The actual conjecture has a weighted form of this where you divide this by P, and here you will get log X, and here you will get big O of 1. Okay. So for example, you can think about Dirichlet L functions for this. So one example which is more intuitive is if LJs are these Dirichlet L functions. In that case, you can see that this Selberg orthonormality conjecture will come from orthogonality of Dirichlet characters. Okay. So we will be using this at some point. So let me try to state the main result upon which we are building. So very recently, in 2017, we have the following result due to Sleitner and Pankowski. Okay, so what we are doing is they take an L function in this Selberg class and fix sigma inside half and 1, and let P be sufficiently large. Okay. Now there are two assumptions. One is that they assume this Selberg, this form that we have stated. So assume the Selberg orthonormality conjecture. In this case, there is only one L function. So we will only need this part, which is when L1 equal to L2 equal to L. So this is one assumption. Second assumption is, okay, and let me also say about this Selberg orthonormality conjecture, all the functions that we know in the Selberg class do satisfy Selberg orthonormality conjecture, and they also seem to be satisfying this strong version of Selberg orthonormality conjecture. So it is believed that everything in the Selberg class also satisfies this conjecture. Okay. So we have this first assumption. Second assumption is slightly more serious. We will say that this zero density, let's count. This quantity is defined as number of zeros of this L function, which satisfy that the real part is to the right of sigma and imaginary part is in the strip 0 to t. Okay. So what we assume about this, we are counting the zeros in a certain strip from 0 to t vertically and to the right of sigma. So what we assume, the trivial bound is t, and we assume this bound t raised some savings, power savings over the trivial bound. So t raised to 1 minus eta for some eta positive. Okay. If you have this, so I'll make some remarks about this assumption a bit later. But if you have these two, then what you see is for any theta inside R, one can look at real part of e raised to minus I theta times log of, not zeta, will be the L function, sigma at sigma plus IT. And if you look at max of this for t between capital T and 2t, then we have an omega result basically that this becomes up to some constant, it is greater than log t raised to 1 minus sigma upon log t. Okay, so this is their result. Let us see what is this actually, what is this left side even telling us? We'll just see. Okay, so what it tells us is the following. Suppose you are going to put theta equal to 0. Then what you get is real part of log of this L function is large. Real part of log will actually give you log of the absolute value of the L function. Okay, and that is large. So what we are having is this takes a large value. What you can say is in every vertical P to 2T strip, what happens is if you try this with theta equal to 0, you will see that the L function is taking a large value. Also, you can also do another thing where you can make the L function small. So if you take theta to be pi, you will get minus of log inside the real part. Here, this will become a minus sign. So minus of log means you're taking log of the reciprocal. So it's telling you something in terms of 1 by this log function, this L function. Therefore, you can say that takes a small value. Okay, so we are really dealing with extreme values, large values, small values, and you can take some intermediate values of theta also if you like. But this is an omega result of this type. So also let me say some things about the assumption. Here, this is a non-trivial assumption, this A2, because this kind of a bound, zero density savings, is not known for L functions in general unless you have sigma close to 1. Okay, so away from that, it is a non-trivial assumption. So up to the point where you have it, you can, have this assumption as upheld, and then you can proceed. That's what we know for now. Okay, so we want to build on this theorem. So what was our question to start with was that this is one L function, and it talks about that L function attaining extreme values in every strip T to 2T. So can we take a bunch of L functions and then ask that all of them should simultaneously take extreme values inside every such strip? So that is our question, and what we prove is the following. Okay, need to. So yeah, right. So our theorem is the following. So let us take L1 to Lk, some collection of functions. Now, instead of Selberg class, we will like to take in the polynomial Selberg class. So we have in S poly. Also, let us take distinct L functions. Only then this question kind of makes sense. You have distinct L functions. You are expecting them to behave independently. So there should be some, they should be taking extreme values altogether as well. So, I mean, that should happen at least in every strip. So let these be distinct. And we are assuming the same two assumptions. So we have Selberg orthonormality conjecture. This time we are assuming we have a bunch of L functions, so we have to use the full strength. And also let us assume this zero density result for each Lj. Okay, this kind of savings. Then what we have is for any theta 1 to theta k inside R, there exists ordinates T1 to Tk in capital T to 2T such that we will look at real value of e to the minus I theta j times log of this Lj, this jth L function at sigma plus I Tj. Okay, and we will say that this will be up to a constant greater than log t raised to 1 minus sigma by log t. This is true for j equal to 1 to k. Okay. If you just stop here, what this means is you are taking L1 to Lk distinct L functions in the polynomial Selberg class. And what we are saying is that in every strip T to 2T, what happens is, let's say I take all the thetas to be 0. Okay. So what we are saying is in every strip T to 2T, these L functions are taking large values at some Tj's, T1 to Tk. The ordinates are different right now. Ideally, we would like to have the same ordinate for all these L functions. Then only you will say truly it's a simultaneous extreme value. But we are not able to do that. But we do the next best thing, which is we bring these T1 to Tks close together. So we say that Ti minus Tj has to be below 2 log t raised to 1 plus sigma by 2 square root log t. Okay, so let me just draw a picture maybe. We have in your critical strip some sigma we have taken. Let's say this is my half. What we are saying is when you look at this T to 2T strip, there are these ordinates at which the functions are taking, all the functions are large, or you can also make all the functions small. But what we are saying is there is a small neighborhood of size approximately log t raised to this power, where all these L functions take these extreme values. So if you want all of them to be large, you will get one particular neighborhood, vertical neighborhood in this strip, where all of them are taking large values. If you want all of them to be small, you may get a different neighborhood, but of the same bounded size, where all of them are taking small values. So let us write these as remarks. So remark is that in every vertical strip, T to 2T, there exists a small neighborhood in which what you can do is in which all LJs are large. You can also do this. This will be done if you take theta j to be 0 for all j. You can also do all LJs small. This is if, again, theta j is pi for all j. You can do whatever you like. Some are small, some are large, so on. So, or a mixture. Or one more thing that we can do is we can also get a small neighborhood in which arguments of all the LJs are large. So we can say argument LJs are large or small. This also you can do. So how would you do this? If you want to get to argument from the log, here we are taking real value. That's why we are getting the magnitude of the function. If you want the argument, you would like to take imaginary value. So to set that up, what we can do is this quantity in front, we can change it to I or minus I. So you have to put theta j to be pi by 2. If you do that, you will pick up the argument of the L function. So you can take theta j to be pi by 2. Okay, so we are getting this kind of as expected, we are getting some independence of these L functions in the sense that their extreme values can be taken together or in whatever combination you like, and the arguments also follow the same principle. So maybe I will try to sketch the proof of this. Okay. So usually from what I see, these results start with a truncation of the L function in terms of a Dirichlet polynomial. So that is our first step. So we do it, we do a certain version of this, it's as a lemma. So what we have roughly I can say is, you look at, okay, let me, so step 1 is estimate LJ by a suitable truncation let S naught be sigma naught plus IT naught. This sigma naught is actually the same as sigma. It is fixed between half and 1. So this one is fixed in your critical strip to the right of the critical line, while this one may vary for now. Okay, so let's say it is free to move for now. We will fix it later. So what we have is log of this LJ S naught plus IT. I'm adding another variable here other than this T naught, some T, which will be in some neighborhood. So we'll say that this can be approximated by, this can be approximated well by a sum over primes close to log T. Let's say between, just we can think of this as between log T and 2 times log T. And what we have here is this coefficient of LJ at P upon P raised to S naught. So we will put sigma naught here and let me put IT naught here. And there is some weight, WP. This happens. So when I'm writing this, this means it's a good approximation. So basically, we will keep reducing this to further and further. I mean, in step 2 and step 3, there'll be more newer expressions like this. And so finally what we get, that we can try to make large or small, and we come back to this. Okay, so I'll just, so this, you can approximate like this for some t inside, let me write down the value. It's between minus tau to tau. And WP is roughly like this weight, 1 minus log P by log P. Okay, and this tau is later chosen as follows. Yeah, log T raised to 1 plus sigma naught by 2 times log T square root. So we have a certain approximation of your Dirichlet function. This is what we start with. Such a version was also used in this result by Christoph and Lucas. Step 2 is the following. So what we do is this P raised to I T naught, we want to get rid of. Remember that right now we have not fixed what this T naught was. It will be chosen later. So let me write this. So our next step is actually, crudely speaking, we are approximating P raised to I T naught by some exponential e to the 2 pi I theta p. How we do this is the following. We take any theta p's which you want to choose later. This is also to be chosen later. Then what happens is, according to this choice, there exists a T naught inside this strip P to 2T such that P to the I T naught approximates e to the 2 pi I theta p. This means we can replace P to the I T naught there by this. How we do this is the following way. This is e to the I T naught log p, right? So essentially what we want is that these two exponents should be close to each other, modulo 1. So we want T naught log p to be close to 2 pi times theta p. So we want theta p minus T naught log p by 2 pi. This distance is the distance to the nearest integer. We want this quantity to be small. And in order to do this, we end up using a result of Chen, which is a quantitative version of Kroneker's theorem on Diophantine approximation. So this will take us into that realm. So we use some result by Chen. This is a quantitative version of Kroneker's result theorem on Diophantine approximation. Okay, so I'm just sketching the steps. So we need to use this in order for this approximation to work. Right now, here again, theta p's are to be chosen later. So in the next step, we'll see what happens. I don't know the statement, but it's like you can take one of the variables is free, and you can, if you give one of them as input, you can approximate the other under certain conditions. So yeah, I can dig it up if you want. So there is, in the statement, there is some, basically this log is what is coming in Kroneker's theorem. And linear independence of logarithms is getting used in the, yes, that one. So here it works, all those conditions that we need, they'll work out and you can do this. Okay. So this is to approximate, to get rid of that PIT naught. So what we have done, if we continue that arrow that we had there, this let us call as 1. Now what happens is 1 has gotten approximated to, using step 2, instead of 1, what we can write is P in this neighborhood of log T, and we have ALJ P by P to the sigma naught, WP. Instead of P to the I T naught at the bottom, we can write e to the minus 2 pi I theta P. Okay. Now, in our last step, sort of last step, what we do is this e to the 2 pi I theta p's, if you see, these are complex numbers of absolute value 1. What we would like to do is replace them by complex numbers of some taking absolute value 1, some strictly less than 1. So what we will do is, now you are given, let's say, arbitrary complex numbers ZP, again to be chosen later. Okay, so you will see when I complete it, in practice we have to go from step 4 back to step 1. That's how your choosing will work. Okay, so given arbitrary complex number ZP with absolute value ZP less than equal to 1, there exists a suitable theta p's inside R, such that this is a sequence, right, over all the prime numbers. So such that what you can do is, if this I'm calling 2, the right hand side, 2 can get approximated as e to the sigma naught, and WP remains as it is, but these e to the 2 pi I things get replaced by ZP's here. So P in this region. This is step 3. Now what happens, what is the advantage of doing this? This behaves like, now you have freedom with these complex numbers that you can choose. This behaves like a random sum. I'm using this very loosely, but what I mean to say is that if you set this equal to something and you want to solve this system for j equal to 1 to k, you can in fact solve it and get these ZPs as solutions satisfying this property. Okay, so that can be shown. We use this Han-Banach separation theorem to do that. But it follows from an idea of good in one of his papers. So what we are doing with this sum, let's say 3, is the system 3 equal to what we wanted on our right side. Actually, there is an inequality somewhere which I have skipped. So you will get greater than equal to, but let's just say equality for now. So we will put what we had in the right side of our theorem, which is log t raised to 1 minus sigma naught by log t. If you want to solve this for j equal to 1 to k, it can be solved. So it has a solution. These equations simultaneously they can be solved, and you can get a solution with these ZPs with absolute value ZP less than equal to 1 being satisfied. Okay, this follows from an idea of good and uses the Han-Banach theorem. So how this proof works in principle is actually backwards. What you will do is we first we write down these equations with these ZPs as variables equal to what we have on the right side. Then you solve this, you are guaranteed a solution, simultaneous solution for this system. So you get these ZPs. Once you get these ZPs, you go to step 3. You have the ZPs. Now, given these complex numbers ZP, you know that there is a suitable theta p which approximates this expression. So these two approximate each other. There are some error terms involved. So you get these theta p's now from step 3. So you come to equation 2. After this, you come to step 2, where theta p's are given to you because you have them from there. Take these theta p's, and then there exists some t naught in this strip such that you have this approximation, and what you can do is from theta p's, you can go to expression 1, which is of this type. Now you fix your t naught, whatever t naught you got from this expression, from this approximation using Chen's theorem in step 2. Okay, so this t naught now gets fixed, and you come back here. Yeah, and this is a good approximation to your L function in a suitable neighborhood. This part is where the neighborhood comes from. And so what you have shown is that this log of this L function is as large as what you had here, because every time you're basically taking care of the error terms and going through. Okay, so this is how the proof works. In practice, it kind of goes backwards. So the only restriction is that actually this will work for any tau. The only restriction in the theorem was tau should be of the order of, less than t naught. So we have to, in order to optimize everything with the error terms, we do have to choose the optimal choice of this tau for us. Turns out to be smaller than the restriction here. So t naught is in the range capital T to 2t, but this small t is moving around in such a neighborhood. So they are both in the, you can say, t naught is here, and what we are saying is t is somewhere in this neighborhood of size 2 tau. So we cannot pin it down. This approximation, first step itself is where, you cannot pin down the exact ordinate. That is why in our theorem, we are not able to fix all the tj's to be the same. We are only able to say that the distance between t1 to tk, they are all closely spaced. This part is coming from that first step. Okay. So I think I'm out of time anyway. So I can stop here.
Thank you for the interesting talk. Are there questions? Questions from the audience?
Yeah, so this Selberg strong orthogonality that you're saying has to be satisfied by any primitive pair, that's it, or if you have just 2 satisfying, then the theorem will apply for 2?
Yeah, if you have, so this k is a variable here. If you take L1, L2, and you have those two satisfying, then you can apply this theorem.
Yeah, so I'm saying if I take any two primitive cusp forms for the full modular group, do they automatically satisfy strongly orthogonal?
I don't know. Do they?
I mean holomorphic because you want Ramanujan.
Yeah. So I don't know offhand whether they satisfy. Do they? I mean, do they satisfy the Selberg orthonormality condition?
Yeah, that's prime sum over prime. So the squares actually Schotterdal proved even for the higher powers with mass forms. I'm sure that proof will work for, but he didn't prove for the inner product. I mean, just for L1 equal to L2.
Okay. Yeah, L1 equal to L2. Yeah, I do.
Okay, so yeah, that has to be checked, I guess, probably.
Yeah.
Okay, thank you.
Yeah. Are there further questions?
So the fact that F belongs to L belongs to S poly is used in this first approximation?
Yeah, it is used. Then I'm saying this, there is equal to plus some error terms. In taking care of those error terms, we are having to use a bound on these coefficients. And it is known if it has polynomial Euler product, then these coefficients on primes, they are absolutely bounded. So we are using that. I mean, ALP is less than some constant for every prime, like the divisor function. So that we are using in the first step. Yes.
Thanks.
Hi, great talk. Thanks for that. I just had a question about the main theorem that you stated. So you have a lower bound and then a bound on the distance. Are they sort of connected? Can you relax one of the conditions and get something else for the other bound? So in the sense that if you increase the distance between DIs, do you get a better bound on the extremal values? Is there some sort of relationship there?
Better bound, I don't think we get. This is sort of expected to be, I mean, what I will say is in the opposite direction. If you want to make this more closely spaced, you get a worse bound.
Okay.
But not the...
Right, yeah. And so is that something that you've already explored?
To make this better.
Or worse, like what is like any sort of relationship between the distance between TIs and the bound?
Yeah, we didn't want to make this worse because this is agreeing, the magnitude of this is, I mean, we already have that for individual L functions, like that earlier result that I wrote here.
Yeah,
so we wanted to, match that at least.
Okay.
So that was why we finally had to compromise on this part.
Right.
But I think, yeah, you can do something like that.
Okay, thank you.
Okay, are there further questions? Yeah, you assume some zero density estimate.
Yes.
And yeah, I wanted to ask, what is known for the Selberg class in general about zero density estimates?
Yeah. So actually, we have. What we do know is for Selberg class, we have t raised to. You have some constant 1 minus sigma plus epsilon. This is we have by Kalsarowski. And I think Perelli. Yeah. And here they are able to get C to be 12 plus 4 times the degree of the function. So this thing is there hindering the this constant. So this is known for Selberg class, but it's not as good as what we want. This is uniformly in sigma half to 1. But there are better results if you are closer to 1.
Yeah. Okay, yeah, thank you. That's what I wanted to know. Are there further questions?
All L functions you are considering in that?
Yes. Here, we will take primitive L functions in here,
So,
because we are doing this. So it is kind of one thinks of these primitive L functions like the prime numbers, like building blocks of the L functions in the Selberg class. So we are doing that. We are taking the primitive function. So I think in a specific case, maybe one could do it for a set of primitive functions and use that maybe to build the large value for the given function that one is interested in. But the issue here, no, I think it would be fine because ordinates still would be, no, maybe it would not work. Yeah, if suppose we had this theorem with all the TIs to be the same, okay, that's what ideally one should get. In that case, if you do it for just primitive elements in the polynomial class, then if you're interested in some other L functions, you can express it as a product of these some primitive elements. Then you can get the large value for that from the product. That is provided, of course, all the TIs are the same. In this case, that is not the case. But hope is that we can build for a general L function using the primitives. You can always express it in terms of a product of primitive elements.
Questions? If not, then